close your eyes for a second. Picture the biggest thing you have ever stood next to. A mountain. The ocean stretching to the horizon. A skyscraper disappearing into cloud. Hold that feeling, that raw, physical sense of being genuinely small against something enormous. Now forget it, because what we are about to talk about makes every mountain, every ocean, every canyon you have ever seen collapse into a single, irrelevant point. Not poetically, mathematically. With confirmed measurements checked and rechecked by scientists using the most powerful instruments ever built, there is a galaxy in the known universe that stretches 16 million light years from one end to the other. A light year is the distance light travels in a full year, moving at 600 million miles per hour. So 16 million light years means light itself, the fastest thing in the universe, would need 16 million years just to cross this structure from one side to the other. That number should already feel wrong, too big, like it cannot possibly be real. That feeling is exactly what we are here to fix. Here is the first problem. Your brain was not built for this. Human beings evolved on a single rocky planet, orbiting a single star. Our entire existence, every war, every civilization, every idea, happened inside a bubble, 8 light minutes wide, 8 minutes at the speed of light. That is the distance from Earth to the Sun. That is the universe your brain was designed to understand. Everything beyond that scale, your mind treats as abstraction, just big numbers without weight. So when astronomers say 16 million light years, your brain nods and moves on. It cannot feel the difference between 1 million and 16 million any more than it can feel the difference between $1 billion and $1 trillion. The numbers lose meaning. They become noise. That is the problem we have to solve before anything else. Let me try a different approach. Imagine you build a physical scale model of the Milky Way, our home galaxy, using a single grain of sand to represent the entire thing. 1 grain sitting in your palm. Now, using that exact same scale, you build a model of the largest galaxy ever discovered. That galaxy is not a bigger grain. It is not a pebble. It is not a rock. It is a boulder, the size of a large car. 1 grain of sand. 1 car-sized boulder. Same scale. The grain does not shrink inside the boulder. It vanishes. You could search that boulder for a year and never find the grain. That is the difference between our home and the largest structure of its kind ever confirmed in the observable universe. Most people carry a mental image of the Milky Way as something enormous, and by everyday standards, it is. But astronomers have spent decades discovering that the cosmos builds things our models struggled to predict, and our intuition completely fails to process. The largest galaxies do not just challenge our sense of scale. They challenge the mathematical equations scientists use to predict how big a galaxy should ever be able to grow, and the largest ones found blow straight past those limits. Every time a new record appears, science is forced to ask a question that sounds almost philosophical. Did we misunderstand the universe? Or did the universe break its own rules? Tonight, we find out. We start here. We start small. And we push outward until the numbers stop making sense in any ordinary way, and something far more interesting takes their place. The Milky Way's real size. Ask someone how wide the Milky Way is. If they remember anything from school, they will say 100,000 light years. That number is everywhere: textbooks, documentaries, science websites. It has become the default, passed down through generations like a settled fact. Scientists confirmed years ago that it is an undercount, a significant one. The 100,000 light-year figure traces the visible disk of the galaxy, the flat spinning plate of stars, gas, and dust that gives the Milky Way its spiral shape. That disk is real. It is measurable, and the estimate is reasonable for that specific layer. The problem is that the disk is only one part of a far more complex structure. And when you account for everything else, the Milky Way becomes a very different object. Surrounding the visible disk is the stellar halo. The stellar halo is a vast, roughly spherical region populated by old stars, ancient suns that formed billions of years ago when the galaxy was still young and violent. It also contains globular clusters, dense balls of hundreds of thousands of tightly packed stars orbiting the galactic center like satellites. And woven through it are stellar streams, long, ghostly trails of stars pulled from smaller galaxies that the Milky Way consumed long ago. The halo is diffuse. Its stars are spread thin. If you floated somewhere inside it, you might see no nearby stars at all, just distant constellations indistinguishable from the view outside the galaxy entirely. But it is absolutely part of our galaxy. Confirmed, observed, and enormous. Measurements of distant stars and globular clusters push the stellar halo out to somewhere between 300,000 and 500,000 light-years from the galactic center. Some estimates reach further. The uncertainty reflects the genuine difficulty of measuring objects that are both faint and scattered across enormous volumes of sky. So before we even reach the invisible component, the Milky Way is already 3 to 5 times wider than the textbook says. Then there is the dark matter halo. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter in any way that our instruments can directly detect except through gravity. It is genuinely invisible, and yet we know it is there. The stars at the outer edge of the Milky Way's disk orbit the galactic center faster than they should. If only the visible mass of the galaxy were generating gravity, those outer stars would move more slowly, the same way the outer planets in our solar system move more slowly than the inner ones. Instead, they orbit at rates that demand additional invisible mass. Mass that is there, real, gravitationally active, producing no light. That mass is the dark matter halo, and for the Milky Way, it extends to somewhere around 1 to 2 million light-years in every direction from the galactic center. The bright, familiar spiral that fills every galaxy poster is buried at the center of a dark matter halo, 1 to 2 million light-years wide. The iconic image is the visible yolk inside an enormous invisible egg. This revision changes everything. The Milky Way is not a 100,000 light-year object. It is a 1 to 2 million light-year object, 10 to 20 times wider than the textbook number, and it is still medium-sized. That is the part that matters for what comes next. Even with the stellar halo, even with the dark matter scaffolding extending millions of light-years in every direction, the Milky Way is unremarkably average by cosmic standards. There are galaxies that make its full dark matter extent look like a footnote. Understanding the true size of our home makes what those galaxies actually are hit harder, because they were not always enormous. They were built over billions of years, through a process violent enough to reshape the physics of entire regions of space. Two galaxies locked on a collision course sounds like the kind of event that ends everything. The reality is stranger, slower, and in some ways, more unsettling than an explosion. Galaxy mergers do not happen quickly. The process takes hundreds of millions to several billion years, from first approach to final combination. The two galaxies spend enormous amounts of time orbiting each other, passing through each other, swinging back around, and passing through again. Each pass distorts both galaxies, pulling stars and gas into long curving streams called tidal tails that can extend for hundreds of thousands of light-years into the surrounding space. During this phase, both galaxies look like they are being torn apart and pulled together simultaneously, which, in a sense, they are. Here is the detail that surprises almost everyone the first time they hear it. The stars themselves almost never collide. A galaxy is overwhelmingly empty space. If you shrank the Milky Way down so that our sun was the size of a grain of sand, the nearest other star would sit over 20 miles away. 20 miles between two grains of sand. That is the typical density of a galaxy. In a merger, two enormous collections of these widely spaced grains pass through each other repeatedly. The grains do not touch. There is simply too much empty space between them for direct contact to happen. But their gravitational pulls on each other add up. Stars that had been orbiting peacefully for billions of years find their paths thrown into new trajectories by the combined gravitational influence of hundreds of billions of other stars, suddenly moving in different directions. The result is chaos, but a slow, majestic chaos, unfolding across hundreds of millions of years. The gas is different. Gas clouds can touch, they can compress, they can slam into each other at full speed. When two galaxies merge, their gas clouds do exactly that. The collision compresses the gas and triggers massive bursts of star formation, millions of new stars igniting across both galaxies as pressure waves move through the colliding material. A galaxy that had been quietly aging suddenly blazes with the light of millions of newly born suns. These starburst events are among the brightest phases in any galaxy's life. They burn hot and fast, exhausting enormous reserves of gas in a cosmically short period of time. Meanwhile, the supermassive black holes at both galaxy centers begin their own slow approach. These black holes, millions or billions of times the mass of our Sun, spiral toward each other as their host galaxies merge. Eventually, they too will combine, releasing gravitational waves powerful enough to propagate across billions of light years. By the time the merger finishes, the spiral structure of both galaxies is gone. The ordered rotating disk, the elegant arms, the flat geometry, all of it scrambled by billions of years of gravitational disruption. What remains is an elliptical galaxy. Stars moving on randomized orbits around a combined center of mass far more massive than either original galaxy. Ellipticals look boring in telescope images. A smooth, featureless oval, brightest at the center, fading toward the edges. No dramatic structure, no glowing star-forming regions. But that understated appearance hides what they actually are. Every elliptical is the graveyard of every galaxy that came too close. And the largest ones, the giants sitting at the centers of massive galaxy clusters, grew by repeating this process dozens of times. Galaxy after galaxy absorbed. Merger after merger stacked on top of each other across billions of years. Astronomers call it galactic cannibalism. And the most extreme cannibals in cosmic history built objects so large they broke the models designed to predict them. In 2022, a team of astronomers published a finding that stopped the astronomy community mid-sentence. They had measured a radio galaxy with jets extending 16.3 million light-years from end to end. The team went back and checked their calculations multiple times before going public. Because the number was so far beyond anything previously measured, that the first instinct for everyone who saw it was that something had gone wrong. The galaxy's name is Alcyoneus, and its size breaks the previous record not by a small margin, it shatters it. To understand why the number matters, you need a comparison that actually lands. The Milky Way spans about 100,000 light-years across its visible disk. Alcyoneus, measured from jet tip to jet tip, is about 160 times that width. If you place the Milky Way inside Alcyoneus, our entire galaxy would occupy roughly 1% of the total structure. 1%. The other 99% is just more Alcyoneus. The previous record holder for the largest radio galaxy had jets spanning about 6 million light-years, already a number that defies intuition. Alcyoneus beat that by more than 10 million light-years. A single discovery expanded the known upper limit of galaxy size by a factor of nearly 3. One measurement, one survey, one instrument finally sensitive enough to see what had been hiding there the whole time. The jets are powered by the supermassive black hole at the galaxy's center. When a black hole actively feeds, pulling in surrounding gas and dust, a fraction of that infalling material gets redirected by magnetic fields into two opposing streams that shoot outward at close to the speed of light. These jets carry plasma, magnetic fields, and staggering quantities of energy across millions of light-years. A single large radio jet carries more total power than the combined output of trillions of stars. Some of the most energetic jets ever measured release the equivalent of billions of supernovae per year, sustained continuously for millions of years. The jets of Alcyoneus have been expanding for somewhere between several hundred million and a few billion years, pushed outward without stopping by the black hole engine at the galaxy's center. When a jet finally dissipates, the plasma it deposited spreads into giant lobes of radio-emitting material. Electrons inside those lobes spiral around magnetic field lines and emit radio waves through a process called synchrotron radiation. And this emission can continue for hundreds of millions of years after the jet itself goes quiet. That ancient, faint radio glow is what the LOFAR telescope network detected. The instrument traced those lobes outward from the galaxy's center and measured the full extent of the structure, 16 million light-years, both lobes, the entire span. Why did Alcyoneus grow this large when other radio galaxies stall far short of this scale? The answer appears to be environment. Analysis of the surrounding region suggests Alcyoneus sits in an unusually underdense pocket of space, a void where the intergalactic medium is far thinner than average. Less resistance means the jets traveled further before losing coherence. In a denser environment, they would have slowed and stopped millions of light-years earlier. The void gave them room that no other known system had. The discovery immediately forced a revision of theoretical models for how large radio jets can grow. And it opened a quieter, more unsettling question. The LOFAR survey was the first instrument sensitive enough to detect Alcyoneus's outermost lobes. Before that survey, the galaxy was known, but its true size was invisible to every instrument that looked at it, which means the question every astronomer is now asking is simple. What else are we missing? Point a telescope at IC 1101, and the image that comes back looks almost boring. A soft, bright oval of light, brightest at the center, fading gradually toward the edges. No spiral arms sweeping outward in elegant curves. No dark dust lanes cutting dramatic lines across the disk. No glowing regions of star formation blazing blue and pink with the light of newborn suns. Just a smooth, ancient, featureless ellipse sitting at the center of a cluster of smaller, fainter galaxies scattered around it like debris around a ship. If you did not know what you were looking at, you might scroll past it. And that would be a mistake. Because what that image is actually showing you, if you know the numbers, is the single most massive collection of stars in the known observable universe. IC 1101 sits approximately 1 billion light-years from Earth. It anchors the center of a massive galaxy cluster called Abell 2029, one of the largest gravitationally bound structures in its region of the universe. And it has been sitting at that cluster's center for a very long time, long enough to have done something extraordinary with the time. The galaxy's confirmed stellar halo, the full extent of its visible stars, reaches approximately 6 million light-years from its center. 6 million light-years, in every direction, from a single galaxy. To put that in the context we have been building, the Milky Way's visible disk spans 100,000 light-years. IC 1101 is 60 times wider. If you place the Milky Way inside IC 1101's stellar halo, it would be like placing a coin inside a football stadium. The coin would be somewhere near the seats. The center of the stadium would be miles away. The star count is where the numbers become genuinely difficult to process. The Milky Way holds somewhere between 200 billion and 400 billion stars. IC 1101 contains somewhere in the range of 100 trillion, that is, 100,000 billion stars. Line them up end to end at the average spacing of stars in our galaxy, and the chain would stretch past the observable universe itself. Where did all of them come from? The answer is not that IC 1101 was always this large. Nothing starts this large. It grew over billions of years. Through the same process of galactic cannibalism we explored in the previous chapter, but on a scale and over a duration that no other known galaxy has matched. IC 1101 has occupied the center of a massive cluster for what scientists believe is close to the age of the universe itself. In that time, galaxy after galaxy, some small, some medium, some large, spiraled too close, was stripped apart by tidal forces and had its stars absorbed into the ever-growing central mass. Each merger added another layer, another contribution to a halo that kept expanding outward, year by billion year. The evidence for all of those past mergers is preserved inside the galaxy's structure right now. If you measure the brightness profile of IC 1101, how bright it is at different distances from its center, you find something that a smooth, undisturbed galaxy would not produce. Instead of a single clean curve, the profile shows subtle changes in slope at different distances from the center. The brightness drops off at a certain rate for a while. Then the rate changes slightly, then changes again. Each of those changes in slope corresponds to a past merger event. When a large galaxy is absorbed, its stars do not mix perfectly with the existing population. They settle into a shell, a new layer of stars at a particular distance from the center, determined by the energy of the merger. These merger shells are a fossil record, a geological stratigraphy of violence, written in starlight. Reading those shells tells you the history of the galaxy, and the history of IC 1101 is a long, relentless story of accumulation. Dozens of merger events stacked on top of each other, each one adding mass, adding stars, adding another ring to the structure. The galaxy we see today is the final sum of billions of years of cosmic consumption. At the center of all of that mass sits the engine that helped build it. IC 1101's central supermassive black hole has a confirmed mass of approximately 40 billion solar masses. For comparison, the black hole at the center of our Milky Way Sagittarius A times has a mass of around 4 million solar masses. IC 1101's central black hole is 10,000 times more massive than ours. 10,000 times. That black hole is currently quiet. IC 1101 is not actively forming stars in any significant quantity. Its gas supply has been largely consumed or expelled by past episodes of black hole activity. The galaxy is enormous, ancient, and still a vast collection of old, red, slowly fading stars, orbiting a center of gravity that contains the accumulated mass of billions of years of history. This state has a name in astronomy. The galaxy is described as quenched. Its star-forming machinery has been shut down. It sits enormous and exhausted, accumulating incrementally from what remains in the cluster environment, but no longer blazing with the activity of its youth. Now, here is the question that stops people cold when they actually sit with it. What would it be like to be inside IC 1101? Imagine our sun, unchanged. Our Earth, unchanged. But place that entire solar system inside IC 1101 somewhere in the outer halo region, about 2 million light-years from the galaxy's center. What would you see looking up at the night sky? The first answer surprises almost everyone. It would look emptier than ours. That sounds impossible. You are inside the largest known galaxy. Surely the sky should be blazing with stars. But the outer halo of IC 1101 is a region where stars are spread thin across millions of light-years. The local density stars per cubic light-year is actually lower than the stellar density in our neighborhood of the Milky Way. You might have no near neighbors at all, just distant points of ancient, cool, red light. No blue giants, no young star clusters, no star-forming nebulae glowing in the dark. The stars around you would all be old. Billions of years old. The universe's most massive galaxies stopped making new stars a long time ago, and the outer halo is the oldest, quietest corner of an already quiet system. But look toward the center, 2 million light-years away. The dense core of IC 1101, containing hundreds of billions of tightly packed ancient stars, would appear as an intensely bright band stretching across a significant portion of your sky, not a smudge. Not a haze, a concentrated glowing river of orange-white light, steady, ancient, overwhelming. And scattered across the rest of the sky would be hundreds of galaxies, the other members of Abell 2029, close enough and bright enough to appear as faint smears of light visible without a telescope. A sky full of entire galactic systems, visible to the naked eye, arranged around you in every direction. It would be the most spectacular and the most lonely sky imaginable. rich with distant light, empty of nearby stars. The center of your galaxy impossibly far away and impossibly bright. That is IC 1101 from the inside. From the outside, it is the largest confirmed stellar system in the observable universe, a monument to time, gravity, and an environment that funneled the mass of 1,000 galaxies toward a single point, over a span of time that makes human history look like a typo. And it is not done. It is simply growing more slowly now than it once did. Pull back far enough and the universe reveals a pattern. Galaxies do not scatter randomly through space. They cluster along thin filaments, enormous threads of gas and dark matter stretching for hundreds of millions of light years. Where filaments intersect, galaxy clusters form. Dense gravitational hubs packed with hundreds or thousands of galaxies, all bound to a common center of mass. And between the filaments lie vast, empty regions called voids, stretches of space hundreds of millions of light years across, containing almost nothing at all. This structure, the filaments, the nodes, the voids, is called the cosmic web. It is the largest confirmed structure in the observable universe, not a theory, not a simulation artifact. A real, mapped, observed architecture of matter, reproduced accurately by computer models of the universe's evolution, starting from the conditions just after the Big Bang. Every major survey of the sky confirms it. The cosmic web is the skeleton of everything, and the material that built that skeleton is something you cannot see. Dark matter makes up the majority of the universe's matter content. It does not emit light. It does not absorb light. It does not interact with ordinary matter in any way our instruments can directly detect, except through gravity. Every large galaxy sits inside a dark matter halo, a roughly spherical region of invisible mass whose extent dwarfs the visible stars by a factor of 10 to 30. Remove dark matter from the universe and every galaxy falls apart. That is not a figure of speech. It is the direct conclusion of decades of confirmed observation. The gravity of visible matter alone, all the stars, gas, and dust combined, is insufficient to hold galaxies together. The stars at a galaxy's outer edge orbit too fast. By the physics of visible mass alone, they should have flown off into intergalactic space billions of years ago. They did not. Because something invisible is holding them in. That something is dark matter. Confirmed through galaxy rotation curves, through gravitational lensing, where massive invisible concentrations bend the light passing near them in precisely measurable ways, and through the large-scale structure of the universe itself, which only matches observations when dark matter is included in the simulations. Remove it from the models and the universe they produce looks nothing like the one we actually live in. Dark matter came first. In the first moments after the Big Bang, it clumped into the earliest density fluctuations and formed the first invisible halos. Ordinary matter fell into those halos next. Gas collected, cooled, collapsed, and triggered the first stars. The first galaxies grew inside dark matter scaffolding that was already waiting for them. Every galaxy we have discussed in this entire journey, IC 1101, alcyoneus, the Milky Way, is, in the most literal sense, visible decoration on an invisible skeleton. The cosmic web is, in effect, a map of that skeleton. Filaments are made partly of dark matter and partly of ordinary gas, primarily hydrogen, flowing along the gravitational channels the dark matter created. Over billions of years, that gas falls toward the densest regions, collects into clouds, and feeds the galaxies sitting at the filament intersections. This is why the largest galaxies in the universe tend to sit at cluster centers, at the nodes where multiple filaments converge. The cosmic web funnels mass toward them like a vast system of rivers, all draining into the same lake. The dominant galaxy at the lake's center gets first access to everything flowing in. IC 1101, sitting at the center of Able 2029, grew enormous because the gravitational architecture of the universe has been conspiring to deliver mass to its doorstep for billions of years. But the cosmic web does not only feed galaxies, it also ends them. When a smaller galaxy falls into a massive cluster, it loses its connection to the filament supply lines that previously fed it with fresh, cold gas. The cluster's hot, intracluster medium, plasma heated to tens of millions of degrees, strips cold gas away from infalling galaxies as they move through it, like water peeling off a car in heavy rain. The galaxy's star formation slows, then stops. It is quenched, enormous, ancient, and permanently switched off. The largest galaxies in the universe are therefore the most fed and the most exhausted objects in existence simultaneously. They grew by being positioned at the convergence of everything the cosmic web could deliver, and they burned through that fuel so completely that they have been quiet for billions of years. Monuments to a violent past, sitting at the center of a structure whose full scale we are only beginning to map properly. And that map, when you zoom out far enough, reveals something about our own position in the universe that no one fully understood until 11 years ago. Here is a question almost no one asks, because the answer was not known until 2014. Where are we? Not on Earth, not in the solar system, not in the Milky Way. We know all of those, but where is the Milky Way itself, in the larger architecture of the universe? What superstructure are we embedded in? What is pulling us, gravitationally, through the cosmos right now? The answer, when it finally came, surprised even professional astronomers. A team led by astronomer Brent Tully published a paper that year that completely redrew the map of our cosmic neighborhood. They were not just measuring the positions of galaxies, they were measuring their motions. The insight was this: if you map how galaxies are moving relative to the overall expansion of the universe, you can identify which ones are flowing toward a common gravitational center and which are flowing apart. Galaxies converging toward the same point belong to the same large-scale structure. Using this velocity flow analysis, the team traced the supercluster containing the Milky Way. What they found was a structure spanning 500 million light-years, containing roughly 100,000 large galaxies, with a total estimated mass of 100 million billion solar masses. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. The Milky Way sits near the outer edge of Laniakea. We are not at the center, we are in the outskirts, a peripheral node in a supercluster we did not know we were part of until a decade ago. The velocity flows in our region of space show our cluster and its neighbors all moving toward a region in the direction of the constellation Centaurus. A gravitational concentration known as the Great Attractor, a point toward which thousands of galaxies across hundreds of millions of light-years are drifting simultaneously on top of the universal expansion. The Great Attractor is difficult to study directly. It sits almost exactly along the plane of the Milky Way's disk, behind our galaxy's densest regions, hidden behind enormous clouds of gas and dust that block visible light completely. Looking toward it with an optical telescope is like trying to see through a solid wall. Radio and X-ray observations cut through that obscuring material more effectively. Over decades of painstaking work, astronomers pieced together the picture behind the dust. What they found was a massive concentration of galaxy clusters, anchored most prominently by the Norma cluster complex, with a combined mass large enough to exert a measurable gravitational pull across hundreds of millions of light-years. The Great Attractor sits roughly 250 million light-years from Earth. And the entire Laniakea supercluster, all 500 million light-years of it, is drifting toward it. But here is the detail that extends the picture one level further. The Great Attractor is itself falling toward an even larger structure several hundred million light-years beyond it. The Shapley supercluster, one of the most massive known concentrations of galaxy clusters in the local universe. So the chain runs like this. The Milky Way moves with the local group. The local group moves within Laniakea toward the Great Attractor. The Great Attractor moves toward Shapley. We are nested inside a hierarchy of gravitational flows, each pulled by something larger, with no center and no end in sight. And then there is the structure that sits at the edge of everything we understand. In 2013, a team mapping the distribution of gamma-ray bursts across the sky found something they could not easily explain. Gamma-ray bursts occur randomly in galaxies throughout the cosmos. Their distribution across the sky should be roughly even, a fair statistical sample of the universe's large-scale structure. Instead, the team found an enormous clustering of bursts, concentrated in a region of sky so large that, converted to a physical scale, the structure measured roughly 10 billion light-years across. 10 billion light-years, in a universe 93 billion light-years wide in total. They named it the Hercules Corona Borealis Great Wall. The reason this finding is so deeply unsettling to cosmologists is not just the size, it is what the size violates. Modern cosmology rests on a foundational assumption called the cosmological principle, the idea that on large enough scales, the universe looks the same in every direction. No special places, no special structures, matter distributed roughly uniformly. This principle is confirmed up to scales of around 1 to 2 billion light-years. A structure 10 billion light-years across breaks that principle directly. Our models say the universe has not had enough time to build something coherent at that scale. The two ends of such a structure have never been in gravitational contact. They should not know each other exists. If the Great Wall is real, something in our understanding is fundamentally wrong. The debate is active. The stakes could not be higher. Step back one final time. Hold the full picture together. You are standing on a rocky planet 8,000 miles wide, orbiting a star 860,000 miles across, located 26,000 light-years from the center of a galaxy 100,000 light-years in diameter. That galaxy contains somewhere between 200 and 400 billion stars and sits inside a dark matter halo 1 to 2 million light-years wide. Your galaxy is one of about 80 members of the local group, a gravitationally bound family spanning 10 million light-years. The local group is one of hundreds of members making up the Laniakea supercluster, 500 million light-years across, already slowly dissolving under the expansion of the universe. Laniakea is drifting toward the Great Attractor. The Great Attractor is drifting toward Shapley, all of it embedded in the cosmic web of filaments and voids that spans the full observable universe, 93 billion light-years from edge to edge. Inside that same universe, alcyoneus stretches its jets across 16 million light-years. IC1101 extends its stellar halo across 6 million light-years and contains a mass 50 to 100 times greater than our entire galaxy system. And somewhere in the direction of Hercules and Corona Borealis, a structure possibly 10 billion light-years across either challenges the foundations of modern cosmology or turns out to be a statistical feature that future data will dissolve. Either answer changes how we understand the universe. The Milky Way, measured against all of this, is genuinely small, not poetically small, not philosophically small, measurably, physically, quantifiably small. Its 100,000 light-year visible disk is a fraction of a percent of Alcyoneus's jet length. Its few hundred billion stars are 1/300th of the stellar count of IC1101. Its position in Laniakea is peripheral. Its role in the cosmic web is that of an unremarkable node in an unremarkable filament in a supercluster that is one of thousands in the observable volume. And we are moving. Right now, as you watch this, the Milky Way is drifting through space at hundreds of miles per second toward the Great Attractor, carried along by a gravitational flow so vast that no human instrument could detect our motion from moment to moment. We will never arrive. Dark energy is stretching the distances between clusters faster than gravity can close them at these scales. But we are moving nonetheless. Participants in a cosmic flow we only discovered 11 years ago. The story is not finished. In 4 to 5 billion years, the Milky Way and Andromeda will complete their slow collision. The night sky above Earth will be dominated by the chaotic merged structure of two galaxies in their final stages of becoming one. The result, which astronomers call Milky, will be a large elliptical galaxy, more massive than either parent, its spiral arms gone, its stars moving on randomized orbits around a merged central black hole carrying the combined mass of both galactic cores. Milky will contain over 1 trillion stars. It will still be smaller than IC 1101. What we will become in 4 billion years is what the universe's giants were at an early stage of their own history. The same process, a smaller scale, a later beginning, and the current records almost certainly will not last. The LOFAR survey that revealed Alcyoneus's true size was the first instrument sensitive enough to detect the faint radio glow of its outermost plasma lobes. Before that survey, the galaxy was known, catalogued, classified, studied. Its true extent was invisible to every instrument that looked at it because no instrument was yet sensitive enough to see the edges. Next-generation radio telescope surveys, already planned and in some cases already underway, will map the low-frequency radio sky with far greater depth. When they do, something larger than Alcyoneus will almost certainly appear, sitting there, enormous and ancient, waiting for the instrument that can finally see it properly. Every generation of telescope has found things the previous generation could not see. Every generation of findings has pushed our models to their limits and sometimes past them. The universe keeps producing surprises when we look harder. There is no reason to expect that to stop. Every number in this entire journey, every light year, every solar mass, every billion-year timescale, was worked out by human beings. Using instruments they built, mathematics they developed, ideas refined through generations of collective effort across centuries of science. The signal from Alcyoneus crossed 3 billion light-years of space to reach our antennas. We built the antennas. We read the signal. We understood, at least in part, what it meant. The largest galaxy we have ever found is 16 million light-years across, ancient beyond intuition, powered by a black hole tens of billions of times the mass of our sun, utterly indifferent to our existence. We found it anyway